Welcome to this interview. I'm David Katzmar from the United States here in Auckland, New Zealand, with Ray Tomes in this office. We're going to be talking about climate cycles, long-term climate cycles. Ray, thank you for this. What will we be doing here today?
Okay, well, we hear a lot of discussion about climate change.
Yes.
And in my experience, the vast majority of people have got no impression whatsoever of the history of climate change. Climate is always changing,
Yes.
always will be, and it changes by huge amounts over long periods of time, and still quite large amounts over shorter periods of time. So the object of this exercise is to give a perspective of the fluctuations of climate and to show that there are in fact recognised cycles in the climate that can explain a fair proportion of the fluctuations that are occurring.
Yes.
So this first one here is a measurement of the carbon dioxide over the last 600 million years.
Phanerozoic carbon dioxide?
That's the one.
Yeah.
So there are some other ones that will show that the level of carbon dioxide in the atmosphere 600 million years ago was more or less what it was in the last couple of centuries. It then rose from 300 parts per million to around the level of 6,000, in other words, 20 times as much carbon dioxide.
Wow.
From where it then fell back to 300 parts per million again, 300 million years ago. Then by 150 million years ago, it was up to 2,000 or maybe even more.
Yes.
From where it fell back to 300 again, a couple of centuries ago, that's what it was, and had been for probably a few thousand years.
Yes.
And from there it's increased in the industrial period to 400 parts per million.
Yes.
Now people have talked about what happens if it gets to this and that and the other thing in terms of the destruction of life. It's important to understand that all the complex life on Earth began to develop 600 million years ago. That's what this period means. And during that time we've had these huge fluctuations, admittedly at a much slower rate than what's happening here right now.
And that life survived that.
And that life survived it, and not only survived it, it multiplied and produced many forms. So vast numbers of different types of creatures. This is where all the vertebrates and all these things developed. And even in these periods where there was lots of carbon dioxide, there were polar bears and all sorts of things, you know. So that gives us a little bit of perspective of the longer term. We may notice that in this period there's a rise and a fall and a rise and a fall in 600 million years. So we can see there's about a 300 million year cycle in the CO2. This is another one, just showing the same thing from a different source and showing similar values, and again a similar one. Now here we've got two things presented together. One is temperature and the other is CO2. We still see the CO2 did this two peaks in 600 million years.
Yes.
But the temperature went up and down, up and down, up and down, up and down 4 times. So it's actually got a 150 million year cycle in it.
So there's no direct correlation here.
And the correlation is not awfully good, is it?
No.
They were both down together here and both down together here. But at this point, you had a low in temperature when there was a high in CO2. And again here, a low in temperature when CO2 was very high. So we can't say definitely CO2 causes temperature.
Yes.
It's much more complicated than that.
Indeed.
This is a more detailed one showing the temperature over 540 million years. Again, we see that there are these 4 cycles. The period is a little under 150 million years. And in fact, we went through a low a little while back. Okay.
Yeah.
So
how far back, right?
Well, that's showing about 20 million years. Some of the others show a little less, but we're at the point where we would expect to be rising CO2 even without any human involvement.
It does seem to fit the pattern.
Yeah. Sorry, that's not CO2. That one's temperature. So we would be on a rising temperature. Yeah.
Yes, change in tropical temperature. Yes, indeed.
Yeah. Another one showing similar things. In all of these, you can see quite clearly both the 150 and the 300 million.
Okay, Ray,
cycles.
and for those of us who might hear this interview and won't watch it as a video, in case they listen to an audio, we're looking at Phanerozoic climate and CO2, Warrior et al.
Now, I'd like to grab a book out of the shelf here, if I can find it. Where is it? All right, I'm just going to mention it. The book is called megacycles. It's the proceedings of a geological conference. It was held a few decades back. It's edited by George Williams, who's a geologist in Australia and has done a lot of interesting work.
Yeah.
But it's the agreement of a lot of geologists present that they found that in geological deposits they found a number of cycles. One of them they say is about 600 million years. We've seen this here.
Again.
Another one is 300 million years.
Again.
And then one they say is about 150 million years, and then 74 million years and 37 million years. Now, we may notice that we're going half.
Yeah.
So we would expect, based on the 37 and 74 are a bit more accurate, we'd expect the others to be just a little less than 600, 300, 150.
Yes.
I had the good fortune to meet Professor Afanasiev from Moscow, the professor of geology at Moscow University.
Yes.
And we'll have another talk at some stage about his method of measuring, dating geological deposits very accurately.
Yes.
But he determined this cycle that the others say is about 600 million, although we would expect to be a little less from the relationships to the others. He says it's 586.24 million years, so we've got a good measure of that. And the others we expect to be half. We're down from that.
Seems to be very close.
Yeah. So there's the global temperature gain. This one's interesting. It's similar to the other one, but it shows this sudden spike at a very short interval, and that KT impact winter 65 million years ago, death of dinosaurs and things.
Of the Paleozoic global temperature we're looking at here.
Yeah, and it may be that one of the suspicions is that some giant meteor or something hit the Earth and caused a mass winter.
Possibly the one in North America.
And this is the sort of thing that might have happened for a very short time, which would have a dramatic effect on life that was evolved for a temperature of this one.
Surely.
And we can see that the temperature range over this whole thing, that's 13 degrees up to 26, 27 degrees. So there's about a 13 degrees Celsius range in temperatures happening over this cycle, and that's vastly more than any temperature changes we had in recent times or are expected from in recent global warming.
Indeed, yeah.
They label the cooler periods here ice house, and the other one's hot house, that we're moving between and fluctuations.
And this is a graph for sea surface temperature anomaly in degrees.
Yeah.
Yes?
Yeah.
Okay.
So we see those. And this has got some interesting text with it as well. I won't read that.
Mm-hmm.
Coming to a slightly shorter period now.
Shorter period for polar ocean equivalent.
Yeah, and
Yes.
this is a 65 million year period.
Yes.
It's measured from the change in the oxygen-18 ratio.
Yeah.
A number of isotopes are affected by the sun and cosmic rays in the upper atmosphere, and are created. And the presence of different levels of them tells us about the temperature at different times in the past, if it gets into things like ice deposits.
Yes.
So, or in other formations, we can look back and see. So those
With the ice cores, they drill very.
yeah, well, they don't go that far back.
Not that far
so
back.
that must be from some other source.
Uh-huh.
But they can measure these changes.
Yeah.
And what we see here again, we're seeing the difference from the present level of temperatures.
Yeah.
It was 12 degrees warmer
Yes.
50 million years ago, right?
Yeah.
So that the changes they're talking about now is things might cause a 2-degree temperature change. So
Much less.
much less. So, and life was evolving many forms in all this period. So we can see that these fluctuations in this area, we're going in and out of ice ages. Right?
Yes.
And we'll come to that in more detail in a little while.
I'll zoom in later.
On that pit, yeah. But what we can see is even the interglacials at this sort of level, this entire 60-something million years
Yeah.
was much warmer than it is now. Okay, so it's only been in the last few million years that we've ever gone below this temperature as we've gone into the glaciations, into the actual ice ages. There have been past periods of that as well, but we can go. The Earth can go for very long periods at a much warmer temperature.
How about that?
Yeah. This is now zooming into that last little bit. We're just looking at the last, this is 400,000 years or so.
And what are we looking at when we see atmospheric and chemical?
Yeah, there's two things. That we've got methane and carbon dioxide.
Got it.
And the red one is the temperature variation.
Yes.
And the black one is the methane. And there's a faint grey one there, which is CO2. It does a fairly similar thing to the methane.
Yeah.
And we can see that they are moving together.
Yeah.
When we get to the present temperature we're at here is that dotted line.
Yeah.
And we can see that about once every 100,000 years, we come above that for a little while.
Yes.
And it's only a short while. The interglacials, this is why the whole period is called ice ages, but the interglacials are quite short, maybe 10,000 years, maybe less.
Yeah.
Well, this one's got a bit longer already, maybe 15,000 years or so, something, approaching that, or 12,000 years. So those are the interglacials. So the temperature we're at now is uncommonly warm over this period, but when we look further back, it's uncommonly cold.
And it seems to be coming towards a high about the time it's due.
Yeah, and things being normal, this would dive any time.
The methane level.
Into both the methane and the temperature would take a dive into the lower levels. But CO2, from what we think is almost certainly human activity, has jumped from 300 parts per million to 400 in this period.
Yeah.
A very, very short period. And methane has gone up by a huge factor. It's actually off the top of the screen here, up there somewhere. So those, we can safely say, I don't think anyone's going to argue that they are not human activity, somehow resulting from human activity.
But CO2 and the methane, yes.
Yeah, and so that's an area to look at further.
Ray, tell me about this methane level that shoots right up in our time right now.
Well, we need to do a research on that, but it's quite clear that it's changed dramatically, and it's presumably the result somehow of something to do with industrial activity.
Yes.
Whether it's taking oil out of the ground and just letting the methane run away and things I don't know.
So it may not be farming alone.
It may not be farming. It may be partly caused by that, partly caused by mining, because they make holes in the ground and the methane leaks out.
Yes, it does.
This is another one showing the ice ages again.
With carbon dioxide
CO2,
variation.
and this is showing how the range over in 100,000 years, the range has typically been 200 to 300 parts per million of carbon dioxide, and we just recently passed 400 parts per million. So we've gone, in a couple of hundred years, we've gone up by as much as the normal variation that's happening in many thousands of years.
And so it is. The Industrial Revolution has caused a dramatic rise in CO2.
Yeah. So I don't think that there's anyone that would seriously state that that CO2 hasn't been influenced by human activity.
Quite true.
Some more graphs of that same stuff. Now, we saw that 100,000 year, let's go back for a moment.
Yeah.
We can see the 100,000 year cycle in the ice ages. We can also see there's some other wobbles going on there.
Yes.
And that Milankovitch was someone who tried to describe why did this happen.
Now, can you tell us what Milankovitch cycles are in a brief description?
Yeah, so that's what we're going to do. So he tried to describe it, and he looked at what are the characteristics of how the heat from the sun arrives on the Earth.
Yeah.
And the different ones he's got here, the top one is the tilt of the Earth's axis. When the Earth's axis tilts more, then the seasons are more extreme as we go around the sun.
Yeah.
When it tilts less, they're less extreme. So this is showing the fluctuation in tilt, and that happens on a 41,000 year cycle. And you can find the 41,000 year cycle present when you analyse those long records. The orbit of the Earth is not circular, it's a slight ellipse.
Yes.
It gets slightly more elliptical and slightly less elliptical over two cycles. One a little less than 100,000 years and one a little more than 400,000 years.
Yes.
So that's showing, you can see the two, you can see the 400,000 one there and the 100,000 one there. Now what effect does that have? It means again that the Earth has a bigger variation in its distance from the Sun or a lesser. So in other words, more extreme seasons again.
Yeah, for two reasons.
Yeah. Then the next last one is the precession. The Earth's axis is rotating like this. On itself, that's not important. It just means which direction from the sun we get summer and winter. But because that comes into conjunction with the ellipse, it's either supporting that, it's either happening, the summer in the northern hemisphere may happen at the moment happens when the Earth is closer to the sun.
Yes.
And the northern hemisphere is more critical than the southern because it's got more landmass around there. And so it has an effect on that. Then what they do is they try to calculate from this the insolation, which means the amount of heat arriving from the sun onto the Earth, and they make a graph of that. And that's the theoretical thing that they would expect. And when you look at what actually happens, it's not the same, right? When you analyse these, you find they've both got the same cycles period present, but this one is much more dominated by the 100,000-year cycle, and this one's more dominated by the two shorter cycles. So this is an outstanding problem. It's generally agreed that these things are relevant, but it's also generally agreed that no one's worked out how to do the calculation correctly yet.
And it's a compound equation too. And I want to make sure I got this right. So there is how much the poles of the Earth will tilt. Then there's the shape of the ellipse that changes as we go around the sun. And then there is the precession of the equinoxes, so it spins around on a nearly 26,000 year cycle. All three, and sometimes it just so happens they all reach what we could maybe call a peak that works together to have much wider changes in temperature.
Or in the heat coming from the sun. But the theoretical calculation on that doesn't agree. That's a generally accepted condition, and various explanations have been given, and they range from one explanation is that those causes are actually solar cycles as well. There are solar cycles of these periods. I don't think that's widely accepted, but it's just a possibility. One thing that I think that hasn't been put in the equation, they're just putting how much heat's arriving on the Earth, but they're not putting how much dust and gas and meteorites and stuff are arriving, which has an effect on the dust in the atmosphere and how much heat gets through. Now, when the Earth's orbit gets more elliptical and less elliptical, when it starts getting more elliptical, it's moving into space where there's a lot of dust and meteors orbiting that it wasn't previously in. It now stretches out into that space. So the 100,000-year cycle, which is the one about the elliptical orbit, and the 400,000, that means that on that cycle you're going to pick up more dust. So the fluctuations due to that cycle would be greater. And that's what we actually observe. Now, that needs to be tested further to see, is that a valid cause? I don't know that anyone's ever researched that. It's just an idea that I had. But it's something that could be looked at.
So how will we translate benthic forums? I don't know. Vostok is one of the places they take the ice core. I presume that's another place where they measured it. Very
well. The main places that these they take ice cores, they drill a big hole down and take a core of ice. And the main places that have been done are in Greenland and in Antarctica. Vostok is in Antarctica, I think.
I'll look into
Vostok is what's there. Yeah, so those, and so the longest ones have been done in about 800,000 years. This is now moving to a shorter timescale again.
And what are we looking at here, Ray?
This is the carbon-14 in the atmosphere. Now, carbon-14 is a measure. It happens as a result of things happening at the top of the atmosphere, turning nitrogen into carbon. So from the sun or cosmic rays and things. And so it's a measure of the solar effect on the Earth. Now, no one doubts that if the sun fluctuates, it's going to affect the Earth. It doesn't mean that all fluctuations that happen on Earth are caused by the sun. There are valid reasons why there may be other things, like, for example, the way the ice is distributed or the way the continents are distributed can affect other things as well. So there's other things in long terms that can have effects. There's ocean current can carry stuff and affect things. So all these things are in the equation. But if the sun varies, we can expect that the Earth's going to vary.
But it will influence us, even though it's not the only thing.
Now this one, a lot of these ones, I try to get the version the other way around, but this one runs from 10,000 years ago to the present backwards. I'm not sure why they do that. I think they don't know how to put the axes that way around. But anyway, so going from the past, we can see that there's this general up and down thing. A lot more shorter term fluctuations as well. But there's this one, and that's a 2,300 year cycle, and that's generally accepted as an existing cycle, that it is there in the sun. but later on, when we talk about planets in the sun, we'll find that there is a 2,300-year cycle of the outer planets' alignments. So that's an interesting thing, and there's been various theories proposed on that. There's no generally accepted position on whether that's the case or not.
Okay, right.
That's one of those other ones of the carbon-14 or something. I've got a better version of that, which we should probably look for. This is a more recent one, and unfortunately we've lost the axes here, but this is showing how in recent times, going back to medieval, so this is the last 1,000 or 1,500 years or something, we can see that there's these successive minimums in the temperature, and recently we've come to a new high, and there's debate about whether that's warmer than this or not, but it's maybe on a par. We may have cracked through that, but that's not the hottest one. There's periods further back where it was warmer.
Yeah, and there seems to be a rhythmic fluctuation.
Oh, there's a rhythmic fluctuation in these ones here. So we can see the shorter term cycles. I'll get rid of that now because I'll mention some other shorter cycles. There's a 208-year cycle that's in the sun, and it's also in the climate. More or less, we can say over recent centuries, it went up during the 20th century, it went down in the 19th century, it went up in the 18th century, it went down in the 17th century. And those ones are quite clear, and it's clearly in the sun as well as in the temperature record.
Yes.
So the 20th century, based on the historical data, that 208-year cycle can be traced back for many centuries. And it's a reasonably regular one.
But in a person's single lifetime, it looks like a direct correlation necessarily with industrial development.
You may think that, yeah. And the 20th century, based on the previous data, would have been expected to have rising temperatures.
But now, even though it probably contributed.
Yes, there may be other factors, but that would have been that would expect it to be rising in that period.
Yes.
Whether it's risen more than that, that's the question. To how much effect did the humans have? There's another cycle that's quite important there. It's not quite as regular as the 208-year one, but it's around about 55, 60 years. And we find that there was a very warm period around about 1940. In that period, the 1930s and 1940, in America they had the Dust Bowl. These bad conditions, and that was quite extreme. And many of the temperature records of different states that were made around that time have not been broken to this day.
Yeah.
So it was a very hot period in America. Around the world, we may have broken some of those, but some of those are still standing. So from that 1940 down to about 1970, we actually had a fall in temperatures. Not a huge fall, but a reasonable fall, to the extent that some of the institutions that are now saying we're going to have runaway global warming were actually predicting, we're about to enter the next ice age. Right?
And that was a prevalent prediction not that long ago, wasn't it? 40
years ago.
Yes.
Yeah. From 1970s, we had a rise again to around 2000. About 1998, there was a peak temperature. That was partly because of the Southern Oscillation Index hitting extremely a very big extreme. And since that time, temperatures have been fairly static.
Yeah.
Now, if we put that 2,300-year cycle in, we've been rising for a few...
It's caused by the planets or on the outside?
Possibly, caused by the sun. We've had a rise that's been happening for some hundreds of years already, and it's going to continue for many hundred years, right? So we've got to put that in the background and say there's this generally rising trend. The 208-year cycle going up and down in alternate centuries at the moment.
Yes.
So we're now into the downside of that, but we're not really seeing a down, even though the 60-year cycle is turning down as well, because the 2,300 is going up. And that's
so we're going up the stairs.
Effect. Yeah, that's right. Yeah, it's like that. Yeah, it's like going upstairs. Now, superimposed on that is whatever humans have done. And I've made some attempts, and I've seen other people make some attempts, to put all those factors together and take the rising CO2 created by humans and so on, and make a regression equation that uses those different cycles and the human effect, human cause, and put those against the long-term temperature record and see how much effect is it.
Ray, let me ask you, a regression equation, what is that, Rick?
What it means is that it's a mathematical technique that when you've got multiple causes to something,
Yes.
you've got a black box and you don't know what's going on in the black box,
Yeah.
and that's what we've got with climate. It's too complicated. People think they can work out models, but their models really don't work.
Yeah.
And what it does is, and you've got a result that actually happens, the temperature, in this case, a number of things that might cause temperature, it will work out an equation that says, take 3 parts of that, 1 part of that, minus a part of that, and so on, and that will give you this. So it works out the coefficients of the equation to make the best estimate of that. And that's the best knowledge we can have. It's a very reliable technique used widely in the physical sciences and different sciences and economics and other areas to unravel the cause and effect of things. So that when we use that for the to estimate what component did the rising CO2 have, you generally get answers somewhere at if we say that's the human effect on the changes in the last century, then you get answers usually somewhere between about 15 and 50%. So I'd say 25 or 30% is a reasonable estimate of how much of the changes in the last century related to human activity.
Yes.
It's I start to think about things like King Canute and the tide coming in, and you can do all the things you want, but if those cycles are going to take us up to there, regardless of what humans change, we're probably going to still go up to there. And if the next ice age comes along, we're going to go down to there. Far further than anything that humans can affect.
So we might have a new stream feeding a harbor, but the ocean is a bigger influence, and that's moving by itself.
Yeah. So that's those are the. I've only mentioned some of the cycles that are present in climate. I've mentioned the ones that are sort of dominant in their range, so that the really big ones which are connected to the geological cycles, the medium-sized ones which are in relation to the Earth and the Sun's motions and so on.
Yes.
And then some other ones that may be related to the other planets, but we're not going to say that for sure. And then the shorter one, there's generally been no theory put forward for the 208-year one for why it happens. Although I did see one recently, someone has something that does look interesting, so we'll see how it pans out.
Okay, but it's still observed, nonetheless.
The cycle is observed. It's very clear they're in all what they call solar proxies. So let's define what a proxy is. Something that you can measure,
Yes.
which you believe is a good estimate of something else that you haven't got the historical records for. We weren't around to measure the accurate output of the sun. It's only been done for the recent decades from space with the satellites, a bit further back, but we've only got maybe 100 years at the most, or maybe a little more, of measurements of how much the sun's output was. Up until 50 years ago, it was called the solar constant, so we didn't know how much it fluctuated, except Abbott, the guy Abbott, did measurements, and he got ridiculed when he said the sun varies.
But recent measurements confirm that it does.
That's absolutely right. We've got measurements from space, very accurate measurements that show lots of fluctuations in that.
Yes.
And people have tried to now. So a proxy is something that tries to measure that by its effect on something else. And we know that as the sun produces more or less solar wind, that affects the cosmic rays coming in. When the sun blasts with the cosmic wind, we don't get as many cosmic rays, and they have an effect on isotopes in the atmosphere. So we get they transmute one element to another. These are very powerful things that come into hit an atom and change it into a different type of atom.
Yes.
And there's a number of different types of atoms that get changed, not necessarily in the atmosphere, maybe on the ground.
And we can detect these levels now.
Yeah, those things. For example, carbon-14. Is not normally existing because it's radioactive. But nitrogen-14 getting hit by a cosmic ray can turn into carbon-14. Then the carbon dioxide in the atmosphere gets taken up by plants.
Yep.
It then gets stuck in the wood. And as long as that's wood, it stays there.
So we can cut a tree and measure levels?
Now, what happens is, over something like 5,700 years, is the half-life of that carbon-14, and it decays. So if you've got a very recent sample of wood, it has a lot of carbon-14. If you've got a 1,000-year-old one, it's got a percentage less. When you get 5,700 years old, it's got half as much.
So we have points of comparison on
Yeah.
the passive influence here,
Yeah.
the sympathetic
Yeah.
effect.
So that's called carbon dating. We use that for carbon dating,
Yes.
and that's good. We can go back maybe 10,000 years or so with that, and we've got those proxies for that. There's some other things go back a bit further. There's some other isotopes that have got much longer half-lives, and you can do longer periods, but you can't do the short periods very well. So these proxies, as far as we know, they're a good measure of something. In many cases, it's solar activity. Some other cases, it's temperature. Some of the isotopes get preferentially selected when ice is forming or something. You get more of one isotope because it's heavier or less heavy or something. Gets incorporated into that. So
Once again, a result that can have more than one cause.
yeah, could have more than one cause.
Yeah.
But they can calibrate these things on recent changes. When there's recent changes, they can calibrate. Does it follow the recent changes correctly? If it does, then it probably did so in the past.
So you can project back with possibility.
Yeah, you can say that we think it was like this in the past. Yeah. So I think that covers fairly much the climate cycles.
It's fascinating. When we look at the climate change and the things that we're talking about, very current in the news, we tend to think of it in very short-term cycles in the last 200-300 years.
Yeah.
But when you look in the long, we really got to fly back from the canvas and get a broader view over time, because a lot of these things are coinciding with cycles.
Yeah.
So it really puts things in.
And I think it's people have said that climate change is an extremely important issue in our time, and I think it's correct to say it's extremely important that we as humans don't make a mess of our planet, right?
Absolutely.
And I don't think there's many people that don't care about that.
Yes.
Some of them think they can get away with a lot more before they has an effect. I've always believed that you should err on the safe side.
Yes.
But a lot of people have made statements, I think, well motivated but keen to cause some change. They've said things that aren't true, and
not everybody has a long-term view on this. So the best way we can take care of the planet is to know how it works.
Yeah, but we should err on the safe side. But we shouldn't say things like that. There's a tipping point that's going to happen now that carbon dioxide has reached 400. We've reached a tipping point. That's a load of rubbish. The tipping point means it's all going to crash. It's going to go run away, hothouse effect. We've got evidence from the past that it doesn't happen.
Yes.
Evidence in the past that when you have 6,000 parts per million, it didn't run away. It came back again.
Yes.
It did take a long time,
Yeah.
but we don't know what the causes of all that is. We don't know what the cause of those cycles is, but they're there. They're real. And that the polar bears are going to be... People were predicting 10, 20 years ago polar bears were going to go extinct in 20 or 30 years. They're not. Polar bears existed through some of those other periods in the past that were much more extreme than now.
That's linear thinking. We expect things to keep going in the direction they're headed, but when you understand cycles, it's a different perspective.
Yeah. So the truth is we don't know very accurately what the human component is. I think we can say accurately, yes, carbon dioxide and methane were caused by humans.
Yes.
But the component that went into the temperature change, there's still a lot of debate about that. And I think we'll cover that as a separate topic.
Yes.
When we get to
but
that.
A lot of things are happening now when they're due, despite the additions that we have to it. This is nothing new. In fact, not only is it not new, it's not as much as it was previous times.
Yeah.
So fascinating.
So this is the intention of this, to give a background so people can look at the things they're being told by pressure groups and politicians and such to see.
Yeah.
Oh, hang on, no, that's not right. Or yeah, that sounds valid, and you can put it against that perspective. So that's the object of the exercise.
Well, Ray Toombs, thanks for looking down the road to see how the traffic is moving and the compound effects of change and explaining it to us in a way that we can comprehend.
Okay.